We're now in Module 4 of Introductory Statistics, and now we're going to be talking about discrete random variables. Basically, we're extending a little bit on the previous module, just as these modules follow from one another. In the previous module, we were talking about different ways to talk about the center and the dispersion of the data. And we're basically continuing that theme here, and we're doing it by talking about different types of probabilistic distributions and about expected values. So, the first thing would be is what is a discrete probabilistic distribution? It's really anything where the probability itself is between 0 and 1, 1 being 100% value of it happening, and that the sum of the probabilities of the individual events is 100%. That shouldn't seem too surprising to you, right? Because if we talk about different possible events happening, like in this case here, how many number of times a week a newborn baby crying wakes its mother after midnight, and in the data we know it's going from 0 to 5 in terms of the observations that we had, that for 0 times it happened 2 times out of 50 for the 50 mothers, 11 times out of 50 where the mother was woken up once, and so on all the way to here. If we add these up to 11, 23, 9, 4, and 1, then we should see here that should equal our 50 options. And alternatively, that if we sum up those probabilities, that it should equal 1. Here's another example where, again, we want to provide the two reasons why this is a discrete probabilistic distribution, meaning, again, that the probabilities are distributed across the, that all the options presented to us are represented in the probability set. This would be number of times that the person rings the nurse during a 12-hour shift, and that 4 patients did it 0 times, 2 patients did it 5 times, so on and so forth. And what we know is that each of these are between 0 and 1 in terms of the probability. We know that that's true. And that the sum of the probabilities, if we add up all these probabilities, that also equals 1. So we know it's a probabilistic distribution. Again, knowing those are the two necessary conditions, we'll be able to tell you either yes or no that this is a probabilistic distribution. Now, the reason why that becomes important is because it's used for determining, among other things, the expected value, which is basically the long-term solution. What is the long-run average or mean? That if we do the things a large number of times, that the law of large numbers dictates what the average would be. So we know, for instance, that if we flip a coin, that this Carl dude flipped the coin 24,000 times, and that he got heads about 12,012 times, which would mean that on average it's getting heads a little bit more often than it is tails. Which is why, again, we said that a fair coin's not exactly possible, that more often than not it is heads than tails. We obviously have a way that we can calculate this. The anticipated value or the expected value, we would simply take the we can represent that expected value with the Greek symbol u, and we can take the summation from 1 to n being the number of cells, the number of segments in the distribution, and that we could then find for each individual cell and its probability, we could add all of those random variables and its probability, and if we added them all up, we will get the expected value. Here's an example here where we have soccer playing for 0, 1, or 2 days a week, and that the probability of 0 days is 0.2, the 20% chance. Probability that they play 1 day, 50%. Probability that they play 2 days being 30%. We know that this is a probabilistic distribution because the sums are each between 0 and 1 and they add up to 1. Now, what's the expected value? To get that, as we see here, and for the exam you'd probably want to do it here rather than in SPSS, we're going to take the expected value, Greek symbol u, is equal to the summation of 1 to n being 2, of each individual value and its probability of occurring. 0 times 0.2 plus 1 times 0.5 plus 2 times 0.3. Getting us 1.1. That the soccer player, on average, over the long run, is expected to play soccer 1.1 times a week. Now, let's go to deck of cards, where you've got 52 cards, and you have to guess the suit of each card before it's drawn. The cards are going to be replaced, meaning we're always dealing with 52 cards. And we've got up to $256 that you could win, and it takes $1 to play. So that would mean that my X values now are either that I could lose the $1, or I get my money back and I get $256. So if there are 4 suits, that would mean that there's a 1/4 chance each time. So the probability of guessing the right suit is 0.0039. That's the probability of guessing the right suit. But now what if I want to know what's the probability of losing? Well, that's going to be 1 minus now 1 over 256. 1 over 256 being the probability of guessing it right, because all the other times it's wrong. 3/4 of the time it's wrong. Leaving me with 0.9961. If I get it correct, going back to the previous slide, 0.0039 times 256 plus probability of getting it wrong times the expected value leaves me with 1/5 of a cent. Which is why, generally speaking, economists don't play scratch-off lottery tickets, because the averages are that the state always wins or the house always wins. Again, I'm not watching these videos. I'm assuming if you're so interested, you can watch them. Now let's look at what binomial distributions are. In a binomial distribution, what we're looking at here is the probability of success or failure. If we repeat the experiment multiple times, how likely is it to have success or failure? The first variable is going to be how many times the experiment is conducted. The second variable is going to be the probability of the expected outcomes. Now, we need 3 criteria to pull off one of these binomial distributions. What we need first is to know that the game is being played a fixed number of times. We need to know that each observation is independent, meaning it's not affected by anything else. And that also the probability of success is independent, meaning it's not affected by anything else. So, we've got our random variable x, that's the number of times of success in n independent trials. Now, what we can do is we can calculate here with factorials, the exclamation point, how many times this experiment, if it's run, what the expected value is. How do I want to do this here? I'm going to skip this. I'm not too worried about you being able to to do this part here. SPSS can calculate this for you, but also the amount of time you're going to encounter something like this is pretty limited outside of this course, unless you're taking an advanced mathematics course here. But now let's look at some ways that we could talk about how useful is the idea of a binomial distribution. So let's say that the State Health Board is concerned about how much fruit is available in school lunches, and that 48% of schools provide fruit every day, 52% do not. So the success is going to be measured as a school that offers fruit every day. Trainer, another example. Trainer teaching a dolphin to do tricks. So dolphin successfully performs the trick 35% of the time, does not successfully perform the trick 65% of the time. Out of 20 attempts, we want to know what's the probability that they succeed 12 times. So this would be a way of saying what's the probability if success now equals 12 times, that we get 12 times in a row. And another example would be, a way of expressing this would be if the fair coin is flipped 15 times and each flip is independent, what's the probability of getting 10 heads, number of heads in 15 flips of the coin. All these are different ways of describing what's going on in the probability. And as I said here, the binomial distribution starts off with number of times we're running this experiment and the probability of success. So n, comma, probability of success. Now, if we look at this slightly differently, and we're looking at about 41% of adult workers have a high school diploma but do not go on for further education. And if I select 20 random individuals, random adults, what's the probability that at most 12 of them, or in other words, in this case 60% of them, have a high school diploma? So how far outside of the range does 60% lie outside of 41%? X being now the number of workers who have a high school diploma but do not go any further. That's our level of success. This is being repeated 20 times in this experiment. Probability of success being 0.41, meaning that the probability of failure is 0.59. So if I want to know the binomial distribution of a game that's run 20 times with a 41% probability of happening, and that I have less than or equal to 12 times of success, that it's easiest just to do this in SPSS, which I'll show you in the next video, that the probability of this occurring should be pretty darn high because the average is already pretty low, that it's as we kind of expected here, 97.38% probability of that being 12 times or less. Not too surprising if the average already is 41% of the event happening. Don't worry about this here. Again, we're not doing this by calculator. Not doing this by calculator. In terms of what this looks like once we know the value here of the 0.9738, that what we should see here, that the peak of this should be our 20 times of happening times the 41% probability, giving us an 8.2 expected value or mean. And that the standard deviation, which we can calculate from the information we had in Module 3, is 2.2. But again, the data, if we put this data into SPSS, we could also get the same result. Don't worry about this. We're not using calculators to solve this. So, if we have an art supply catalog that has 560 pages and 8 of the pages have signature artist. Now, let's say that I take a random sample of 100 pages. How many of those pages are going to have signature artists on it? So what value will the x take on? That would be 0 to 8. Either I have 0 pages, 1 pages, 2 pages, all with these signature artists. I have 100 pages, that's my n. And then I know that the probability of success is 8 over 560. Instead of having 8 over 560 as a ratio, instead I could just have the actual percent. How we can extend this further is, what if I want to find the probability that 2 pages feature signature artists? What's the probability that 6 pages feature signature artists? Or what's simply the probability that at least more than 3 pages feature signature artists? Well, now we can actually calculate these things out. Again, you're not going to need the calculator. You don't even really need to use the formula. I'm going to show you how to do this in SPSS. Now let's look at the geometric distributions. In the geometric distributions, what we're doing here is we're trying to find a way to, well, essentially, if I do something a certain number of times, what's the probability that I'm going to get it on the 5th try, not even knowing, or the 6th try, or whatever, not knowing how many times the event occurs. So let's talk about what that would look like. All geometric experiments, like the Bernoulli trial, which is essentially a binomial distribution, what you need to do is you need to know that the experiments could be conducted for infinity, but there has to be at least one trial being conducted, that the probability of success is the same each time around, and that if you repeat this, each time you repeat it, that each time the event happens, it does not affect the other times that it's occurring. Now, we can understand this with a game of chance. What's the probability that it takes 5 games until you lose if there's a 57% chance of losing? Well, if there's a 57% chance of losing, there's a 43% probability of winning. And if you play this game 5 times, what the probability is of winning it 4 times and losing it the 5th time, right? In this case, if you play the game 5 games and on the 5th time you lose, because after you lose you don't play anymore, there's a slightly under 2% chance of that occurring. Not very likely. We could also repeat this for how students do on a exam. And if the instructor feels that 15% of the students get less than a C on their final exam, she wants to look at exams until she finds one that has a grade below a C. How many what's the probability that if she looks at least 10 exams, how likely is it that she's going to find one at less than a C? Not that unlikely, 23% chance, with again the binomial distribution that, again, you're not going to be responsible for actually calculating here. For the distribution function, again, this is something that SPSS can do the work for us, so don't worry that much about it. Okay. More important for this one will be me walking you through the SPSS instructions for this. So I'm going to stop this video at this point, and then we can work through the distribution, how these distributions, how you're going to calculate them for the homeworks or for the exams.